Okay, good afternoon, everyone. Good evening, everyone. I welcome you to the third live session of the NPTEL course, Oil, Hydraulics and Pneumatics. The tutor for this particular course is Professor Somsekhar S. Hiramat from the Department of Mechanical Engineering, IIT Madras, and I am Arnab, the teaching assistant for this particular course. I hope that you have gone through the lecture videos of the third week and also week one and week two. And in today's session, we'll be discussing a few questions from the topics that were discussed in the lecture videos of the third week, mostly concerning pumps, different types of pumps, the characteristics of pumps, the disadvantages and the advantages associated with it, and a few numericals. If you are having any doubt, you may please come up with the same and we can have a discussion. Okay. Let's move to the first question. Okay. So, which of the following are not a type of hydrostatic pump? So, what do you mean by the term hydrostatic? Hydrostatic basically means it is a positive displacement pump. So, positive displacement pump. So, which of the following are not a positive displacement pump? So, G-rotor pump. We know it is a generator rotor pump, also known as G-rotor. It's a positive displacement pump. Then coolant pump is used in pumping coolants. So generally, centrifugal type pumps are used to pump coolants. So centrifugal pump is a hydrodynamic pump or non-positive displacement pump. So coolant is also generally a type of coolant pumps are also like centrifugal pumps. Radial piston pump. This is also it is a type of a reciprocating pump, so it's a positive displacement pump, so that is not a correct answer. Then water pump is also it can be like reciprocating type, or it can be centrifugal type depending upon the applications. So uh, centrifugal pump is generally a hydrodynamic type of pump and not a positive displacement pump. Coolant pumps also like we may use. So these two are correct answers. Some water pumps are hydrostatic pumps, so we can't say that these are not hydrostatic pumps. Which of the following are not the features of hydrodynamic pump? So as I already said, hydrodynamic pump is a non-positive displacement type pump. So yeah, which of these are not the features of hydrodynamic pump? It pushes the fluid through centrifugal action. Yes, it is one of the key or prime features of hydrodynamic pump. No gap between rotor and stator and no elastic deformation. So we this is also not correct, because we know that in a hydrodynamic pump there has to be sufficient gap between the rotor part and the stator part, that is the pump housing and the impeller. So you have the impeller rotating, and it will suck the fluid, and it will throw it out into this basin, and the kinetic energy of the rotor will get converted into the pressure and kinetic energy of the fluid, and that will get pumped out through this particular section or the outlet. So as you may notice that there is a clearance between and this clearance is considerable between the stator part. Stator part is the housing, because it is stationary, and this is the rotor part. It is rotating, or the, I would say, impeller, right? So there is a considerable gap. So there is a large clearance space between the rotating element and the stationary element. So this is, oh, sorry, this is not the correct option. Rather, this is a property of centrifugal pump. No, this is not a feature. Then low pressure and high volume flow, and high pressure and low volume flow. So generally, we know that since this is not a positive displacement pump, hence it is incapable of producing, um, incapable of working against high heads or against high pressures. So it is generally used in low pressure applications, but it can produce a large volume of discharge. So low pressure and high volume flow is a feature of hydrodynamic pump, but high pressure and low volume flow is not a feature of hydrodynamic pump. So these two are the correct options. Okay. Now coming to the next question. Okay. So just now we discussed about hydrostatic and hydrodynamic. As I already mentioned, hydrostatic is a positive displacement pump. Hydrodynamic is a non-positive displacement pump. What is the difference between this? How do we identify whether a pump is a positive displacement type or a non-positive displacement type? And according to applications, how do we choose that? So, generally, by definition, positive displacement pump, it positively discharges a fixed volume of the working fluid per cycle or per rotation, per revolution or cycle. So whatever be the backing pressure, or whatever be the head against which it is acting, it will try to produce a fixed quantity. It will try to produce a fixed discharge. Whereas in case of non-positive displacement pump, it depends on the head. So this is independent of head against which the pump is pumping the liquid. It doesn't discharge a fixed volume of working fluid. So this Q is variable and depends on head. So as you may understand that if you are working against high loads, then if you're working against high loads or high pressure, then this type of pump is not suitable. Okay, like non-positive displacement pumps are not suitable. Whereas if you're working against low pressure heads, but we want to discharge a large volume of working fluid, then your non-positive displacement type pumps are most suitable for such applications. Okay, so one more thing, like how do we say that whether this discharge is fixed, like the volume of liquid that is being pumped, that is fixed or that is variable? How do we ensure that? So that depends on completely the design features of the pump, the dimensional and the shape of the different parts that are being used inside the pump. We design the pump in such a way that whatever be the head acting on it, provided there is no leakage or like less leakage. um, the discharge is more or less constant in case of positive displacement type pump. Coming to the next question. So, okay, so we are discussing about pumps. We know that there are certain assumptions that we need to arrive at the analytical um, you know equations and all. While solving some numerical problems, we need to arrive at some formula. So while designing the pump, we have to make certain assumptions. So one of such assumption is that the pump is ideal. So under what circumstances do we consider the pump to be acting as an ideal pump? It is saying that there is no gap between the rotor and stator, and also there is no elastic deformation. So yeah, that is one of the features of an ideal pump, because if there is elastic deformation, then the leakage will be happening between the mating parts, or between the rotor and the stator. There will be some gap, and the leakage from the high pressure side to the low pressure side can occur if there is elastic deformation, if there is a gap between them. And if there is elastic deformation, you can understand that the differential pressure can cause some sort of you know bending of the component of the pump. So that is not desirable. So that is not a property of an ideal pump. So no elastic deformation and gap exists between the stator and rotor. That this is not correct, because the first one, no elastic deformation and no gap. Again, this is not correct. The theoretical flow rate is independent on differential pressure across the pump. So theoretical flow rate is basically the volume of liquid, the volumetric displacement into the RPM. So for an ideal pump, we know that it doesn't depend on the differential pressure acting across the pump. Suppose this is your pump I am showing. So the head against which it is acting, that is the difference between the P in and the P out. So whatever this value is, it is dependent on the load that is acting. It depends on the load that is acting in the hydraulic circuit. Suppose it is lifting something, or it is mm, you know carrying something, or it is clamping something. Like in the hydraulic circuit, you are having some actuators that are doing this type of activities. And in such cases, the fluid flow, it is happening against the particular load. So the pump is also pumping the liquid into the hydraulic circuit against a particular load. So that load determines the value of this delta P. And yeah, in case the pump is ideal pump, this the for in case of a positive displacement pump, this QT is independent of delta P. Okay, so only if this is a positive displacement type pump, then this particular option is correct. In case it is a non-positive displacement type pump, this is incorrect. If we Okay, so we have one question relating to this in the upcoming slides. So we'll discuss in detail regarding this. So as of now, we can consider that the theoretical flow rate is independent of the delta P. For, I'm again mentioning here, positive displacement pumps only. Because in case of non-positive displacement pump, what happens? If the pressure at this particular point, I'm showing it in green color. If the pressure here, like this is the outlet pressure, it increases, then there will be some of this liquid that will flow back here. Like it will recirculate inside this housing since there is a huge gap. And that recirculated volume of liquid, that is dependent on this P. Higher the value of P, higher will be that loss component. So you can understand that for non-positive displacement type pump, it this is dependent. This is this value of Q is dependent on P. But for ideal positive displacement pump, both of this holds good. Coming to the next question, which of this is an axial flow positive displacement pump? So in case of positive displacement pump, the flow can be happening perpendicular to the axis of rotation of the rotor. So flow is, in case of axial flow pump, it is parallel to the axis of rotation of the rotor. Okay, and in case it's perpendicular, like in case of screw pump or sorry, like in case of gear pump or vane pump, then it is not an axial flow pump, right? Which of the which of this is an axial flow positive displacement pump? Gear pump, as we know, like the axis of the gear is perpendicular to the direction of flow. Yeah, this is your this this doesn't look like a gear at all, but still, just assume this is a these two are gears. So you can understand that the axis of this gear, it is passing through this point and perpendicular to the plane of this paper, and the flow is happening. Suppose it is rotating in this direction. So here at this portion, the unmeshing is taking place. The gears are going apart. So here the pressure will be less. So this is the inlet, and here meshing is taking place. So pressure will be more. So the outlet, and here you have a suitable housing, right? So can understand that the direction of rotation of, sorry, the axis of rotation of the rotor, which is perpendicular to the plane of the paper, uh, that is perpendicular to the flow. But in case of screw pump, in case of unbalanced or balanced vent pump, also same thing is there. In case of screw pump, that is not the case. In case of screw pump, you have a screw like this, which is rotating, and yeah. So what happens? As it is rotating, it pushes this particular volume of liquid is pushed to the like it is pushed forward, but upon one rotation of the screw, and again this is pushed here. Like I'm just showing it. This is the path it follows. Like as the screw rotates, like this it goes, and uh, ultimately it moves forward. So here you can understand that if this is your if this is your axis of rotation, then the direction of fluid flow or direction of discharge is parallel to the axis of rotation of the rotor. Okay. Again, in case of piston pump, we can't say it's a axial flow type, right? Yeah, we can't say it's an axial flow type, but yeah, screw pump is an axial flow type positive displacement pump. Okay, fine. Moving on to the next question. Huh. I just drew the internal gear pump here, right? So the next question is concerning that only the clearance between the gear teeth tips and the pump housing. So these blue colored ones are the gear tip or gear tooth, and the red one is the pump housing. So the clearance between the tip of the teeth and the housing. So this particular distance they're talking about in an external gear pump is in the order of 5 mm, 2 mm, 0.25 mm, 0.025 mm. So as we know that this is a positive displacement pump. So what happens when this is rotating? This particular gear is rotating. Suppose a particular stream of liquid is getting trapped here. So when the gear rotates, it this particular pocket of liquid will also move along with the rotation of the gear, and accordingly, it's like when it comes here, its pressure increases and it gets discharged in the forward direction, right? And some of the liquid may get, a very small quantity of liquid may seep through this um, mating gears. So you can understand that here the liquid is getting pressurized. Like the pressure of the liquid at this particular point is less than the pressure of the liquid in this pockets. So if there is a clearance, if there is a clearance between these, you know, one second. If this clearance is exist like it's considerable, then the pressurized liquid will try to flow back here because the pressure at this point is higher compared to the pressure at the inlet. That's why we need to avoid that leakage, avoid that backflow of liquid from high pressure to low pressure zone. We keep the clearance as less as possible, but at the same time, we need to give this clearance so that the gear rotation is not interfered by the housing. Also, there may be some thermal expansion and contraction happening. So accordingly, we have to design the gear and the housing. Generally, the tolerance, it is a very close tolerance, and the clearance is kept at around 25 micrometers or 0.025 mm. So you can understand it is very, very less. So the diameter of a human hair is approximately 100 microns, 100 to 200 microns. So you can understand 25 microns is one fourth of that dimension, one fourth of 100 microns. So yeah, it's very less. Okay, coming to the next question. So this was your correct option, basically. What is the role of a crescent shaped divider in internal gear pumps? So what I discussed now was an external gear pump because there are two mating gears that are externally mating with each other. In case of internal gear pumps, we have two gears which are internally mating with each other. Okay, so So these are your these darkened ones are the teeth of your outside gear, right? External gear. I won't say external, rather the ring type ring gear. And so this is your ring gear, and this is your driving or pinion gear. So again, here this and there should be some eccentricity between the center of the ring gear and the center of the pinion or the driving gear for these gears to be meeting, right? So I'm considering this is the center. Okay, so if this is rotating in this direction, then the ring gear will also rotate. It won't be stationary. So there should be some housing. Uh, Sorry, that fit should be very, that close fit. You can't have much clearance. Otherwise, there will be leakage of liquid. Okay. So what happens again when this particular, you know, sorry, when this particular pinion gear is rotating, it tries to, sorry, it meshes with the external gear or the ring gear, and at this particular position, you can see that the volume it is expanding. So if I'm considering this to be um, del- some small volume, say delta V, so this delta V is expanding. So that's why the pressure is reducing and the suction takes place like this. If we put a pipe here, then the suction will take place at this point. And as the liquid flows through here, what will happen? The liquid will, with the rotor, it will, the liquid will try to flow through this gap. And at this particular position, where the gear mates with each other again, there the pressure increases because here the volume decreases and hence the pressure increases. So here we keep the outlet. Now tell me whether this is correct or not. Like whether the flow inside and the flow outside will be happening at a desirable manner or not. It won't happen. Why? Because you have a pressurized liquid at this zone and an unpressurized liquid at this zone. So obviously there will be backflow inside the pump itself, right? So to avoid that, we put this crescent shape divider. So it's a divider like this. So what is the work of this divider? You can see that it divides the flow here at this position, like just after the liquid is been sucked in, it is dividing the flow. So some amount of um, pressurized liquid will flow through this pocket and some through this pocket, and again they will merge here. And since the space is reducing in this region, the pressure will increase. So what happens? This allows the liquid to be positively displaced along this direction. It doesn't allow the liquid to flow back due to the delta P, right? It allows the liquid to flow around this direction only through these small pockets. And again, the clearance here plays a major role. The clearance between this meetings, this gear teeth and the crescent, and again between this gear teeth and the crescent, it should be um, around this range. Otherwise, like if it is more than this, then there are possibility of the pressurized liquid to flow backwards. If it is less than this, then wear can take place. So that plays a major role. So this is the role of the crescent shape divider. It acts as a seal between the discharge and the suction ports. So this is your suction port and this is your discharge port. So here to here, it acts as a seal and it prevents the backflow of liquid. If this crescent shape divider was not there, then we couldn't say that this was a positive displacement pump. Okay. So till now we were discussing only theoretical questions. So let's come to some numericals. So this numerical is already discussed in one of the lectures, but still I have taken up this numerical. Why? We will get to know. So the question says calculate the sorry, theoretical delivery of a gear pump. So if nothing is being mentioned, whether it's an internal or an external gear pump, you can assume it's an external gear pump only because in case of internal gear pumps, um, you have to be like you need to be knowing the dimensions of both the gears because they are not equal. In case of external gear pumps, the dimensions of both the gears, the two gears are identical. Okay, so a module of the gear teeth is 6 mm. So I'm just noting it down. M is 6 mm. I'm converting it to the width of the gear teeth is 65. So W is 65 by 1000 meter. Number of teeth on the driver gear is 16. So let's say N is equal to 16. Pressure angle is 20 degree. So I hope you know what is pressure angle. If two gears are meeting, then this the line of force exerted by this teeth onto this teeth, that is called the pressure angle. Like the angle between that line and the perpendicular passing through the meeting point here, the intersection of the two peak circles on that perpendicular. This angle is called pressure angle. That is basically 20 degree. The pump speed is 1600 RPM, revolutions per minute. Outer diameter is given as 108 mm, and dedundum circle diameter can also be considered as the inner diameter, that is 81 by 1000 meter. So they have also mentioned volumetric efficiency as 0.88 and the head against which it is acting is 7 megapascals. So the question has asked you the theoretical delivery. So what is theoretical delivery? It is the theoretical discharge. QT is nothing but the volumetric discharge, which is theoretical, into your RPM. Right. Now you can apply two formula here. One which is simple, like pi by 4 d outer square minus d inner square into W. This is the width of the gear, and these two are also known. So, what value are you getting? Can you please help me with the calculation? What is the value that you are getting here? I hope that you're also solving the numericals, right? Because you can expect this type of questions to come in exam. Okay, so d outer is 0.108 square minus 0.081 square divided by 4 multiplied by pi, again multiplied by width, that is 65 by 1000, 0.065. So you're getting somewhere around 0.0002605.26. This is meter cube and not meter cube per bin. So your discharge will basically be Vt cross N. And so your N is 1600 revolution per minute. So you just multiply this with 1600, you'll get 0.417 meter cube per minute. Correct me if I have done any calculation errors. So this is one of the approaches. You also have another formula which directly gives you the value of Qt, but that is like that is formulated based on the design parameters, right? So that formula was directly given. So I have denoted number of teeth by small n. Okay, so this is your pressure angle. Fine, if we substitute the values, just let's cross check once. So this is nothing but, if you just carefully see, if we just remove this particular n, then the remaining terms is what would be the uh, volumetric displacement, right? Okay, so yeah, uh, let's just plug in the values. 2 pi into w. W is 0.065 cos m square, that is 0.006 square, multiplied by 1600 rpm, multiplied by did a mistake. So your n is nothing but 16 plus I square cos square alpha. I square divided by 12 multiplied by cos square alpha. Alpha is your 20 degree. So if you also calculate this, you will get the same result. But it will be slightly higher than this one. Like if I round off, it will be 0.417 only, slightly higher. Okay. So this type of questions you may expect in your exams. So why like why did I discuss this problem? Basically, if you look at the configuration of an external gear pump, that is this one, then you will find that so if this is you know like I'm just considering one particular gear, say this one. So if this half is like half of one gear, say, and this half is half of another gear. So pi d outer square by 4 is nothing but, say, if you consider this part of the gear, is half of the gear, and this is the outer diameter or the addendum circle diameter, then d outer square pi d outer square by 4 will give you the area of both the halves of the gear, like this half and this half, right? And if you subtract the internal circle diameter for both the halves, then you will get pi d inner square by 4. So that is basically this annular section through which the liquid is circulating, right? So that is the displacement volume. So in case we are not given with the values of say this particular values, d outer and d inner, then this is the way of approaching the problem. This would be like more accurate because it takes into consideration the role of gear teeth, right? But here, if we look into this particular, sorry, if we look into this particular thing, it is simply like it is considering a hollow annular section. This is your inlet, this is your outlet, and it is having some width, say W. So simply the liquid is coming and circulating through this annular section and getting exited to this port. So that volume of liquid is being considered per cycle and sorry, not per cycle, per revolution. And if when you're multiplying it with RPM, then you're getting per minute. What is the discharge? So it is not taking into consideration the design, sorry, the parameters of the gear when you're taking the first formula. But in the second formula, it is considering the parameters of the gear. This one, this blue colored one. So according to me, this would be a more accurate approach. Although this formula is also a simplified one, and like it has been calculated, so still like this is taking into consideration the gear parameters. Calculate the theoretical delivery of a gear pump assuming 1500 rpm. N is given as 1500 rpm as pump speed, 100 mm as the outer diameter of the gear. Again, same type of problem. So 0.1 meter and inner diameter is 0.08 meter, the dedendum circle diameter. I hope what is addendum, you know what is addendum and dedendum. Suppose this is the gear tooth, one gear tooth, and there are other gear teeth also. So from the center, this particular distance from the center is called the dedendum circle diameter, and this circle is called the dedendum circle. And if you take this outer circle that moves through the tip of the tooth, then this is called the dedendum circle, and the distance from the center, that is the addendum circle. Sorry, this is the addendum circle, and the distance is called addendum circle diameter. And this is what we have denoted by outer diameter, and this one by inner diameter. So as we have seen, the liquid will be flowing through this particular pocket. So yeah, um, you have 60 as the width of the gear too, so 0.06, and your volumetric efficiency has been given 0.86, 10 MPa. Again, they have asked the theoretical delivery only. Also, so theoretical delivery, we know it is theoretical volumetric displacement into N. We'll just plug in the values. Again, we are just considering the annular space between the outer and the inner circles, imaginary circles, into W plus N. So what will be the answer here? Come on, you should also calculate, right? So we have pi by 4 multiplied with the outer square. So that's zero point 0.1 square minus 0.08, right? Yeah, 0.08 square multiplied with W, that is 0.06. That will give me VT. So that's coming out to be 0.00017. And when we multiply it with RPM, it's 1500. So we get 0.254. 0.254, this one, meter cube per minute. So this is your theoretical efficiency. If you are asked what is the value of actual efficiency, then how should you approach? Actual efficiency is less than theoretical efficiency because there will be some amount of loss which occurs through either through this clearance or while the two gears are mating at that part also. Suppose this is one gear and this is the other gear. Sorry. Pardon me. So from here also some liquid will, you know, come from the high pressure region to the low pressure region. So some liquid will also flow back through here. So this leakage and the leakage to the clearance will account for the Q loss, and they will get QAC less than Q theoretical. So let's the question hasn't asked. Let's see. Like you have all, you can also note that the volumetric efficiency is close to 90%, like 80 to 90%. So 10% or 15% of the fluid uh, was lost in the form of losses. So QAC is your 0.86, that is 0.254. How much is that? That's 0.218 meter cube per minute. So you can see that this is your actual flow rate. Okay. Now one more thing. You in the question, like you have been mentioned this particular candidate, that is delta P. That is the pressure head against which the pump is acting. Again, let me just denote here. Suppose this is your pump, this is the outlet line, and this is the inlet line. So the difference in pressure between the outlet and the inlet is your delta P. This is the pressure against which your pump is pumping the fluid constantly. That is 10 MPa. That is not used in this entire calculation. So this is because initially, like we just discussed, that this particular QT is independent of delta P. So if we just try to, you know, see the graph how the delta P versus Q looks like at a given speed, at a given speed N1, say, ideal for ideal pump, this should be how the curve looks like. At a higher speed, say N2, it should be like this. At more higher speed, N3, it should be like this for ideal pump. So N1 is less than N2, less than N3. N2 is less than N3. So we can understand Q theoretical. So these all three are QT. So they are directly proportional to N, but independent of, sorry, delta P. But I have calculated this actual value of discharge. So here I have used this particular parameter, that is the efficiency parameter. When for actual pumps, this efficiency basically depends. This volumetric efficiency is dependent on, is a function of delta P beyond a threshold value. I'm telling PTH. So beyond a particular pressure, the volumetric efficiency starts decreasing as the delta P is increasing. Why? Because when the pressure is excessively higher, there can be some elastic deformation of the components, and there are higher chances of the liquid seeping in from the high pressure to the low pressure. So that is also known as the oil seepage. So these two phenomena occurs when your pressure head is beyond the rated pressure. So that's why every pump, be it an external gear pump or any pump, it comes with the manufacturer's catalog, and there you have been mentioned about the rated pressure. So you should be using that pump for such applications where the expected pressure range will be less than the rated pressure. Only then you can expect it to be working at a particular volumetric efficiency. So I just explained this as an extension of this problem. It doesn't concern this particular problem, but just as a theory, I just said. Okay. So the next question is connected to this particular discussion. Which of the following graphs correctly represent the head versus discharge graph in an actual positive displacement pump? So for an ideal positive displacement pump, this is the, by the way, this head is nothing but the delta P. It is generally represented in the dimensions of length scale, that is meter. So let me just tell you, delta P, say it's rho g h. Rho is the it's the density that we are using. G is specific gravity, and h is the head that we are talking about. This head. So h is delta P by rho g. So at any head, at a at a particular speed, whatever be the value of delta P, the discharge will remain constant for an ideal pump, ideal positive displacement pump. As I had discussed now, like QT is not dependent on delta P or head. Okay, head means this H. But in case of actual positive displacement pump, what happens? As the pressure increases at a particular velocity, I'm talking about, as the pressure increases, there are chances of elastic deformation of the components and also leakage happening between the mating parts, like between the in the clearance of the gap between the mating parts. So due to that, QL comes into picture. QL is nothing but the difference between the theoretical and the actual value of discharge. So due to QL, your actual discharge reduces. So as delta P increases, this QL is also increasing. The volumetric loss of discharge, or the loss in the volumetric discharge, that is also increasing as the delta P is increasing. As a result, your Q actual, it reduces, because Q actual is nothing but Q theoretical minus QL. So if QL is increasing, Q actual will obviously reduce. So as delta P increases, Q actual reduces at a particular speed. So this is all at a given RPM of the motor. If the more RPM of the motor is changing, then obviously your discharge will change. So yeah, between these two graphs, you can see that this correctly depicts. So if this was your Q theoretical, the Q actual is shifting because, okay, so I should have marked it using a different color. This is your theoretical and this is your actual. And this particular deviation at a given pressure, say delta P, this is the particular value of QL, right? This is not correct. And this is for ideal pump. So this is the correct option. And these two are incorrect. So, yeah, can you tell me this particular head versus discharge curve is for which type of pump? Anyone? This particular curve depicted here, it represents which type of pump? As the discharge, as the at a given head, you can see the discharge is constant, but like beyond a particular value of discharge, it is this pressure, this head is reducing. Generally, this is for centrifugal pump. I'm sorry, like at a given so as the you know like the pressure at a given pressure head, your like discharge is increasing. That's what. And beyond a particular value, it again starts falling down. Like the pressure is reducing. That's what we had explained in the initial lectures. Like if like the discharge is like we can increase the discharge up to a particular point beyond which the head at which we are and there will be some sort of like backflow happening. This is again incorrect. This is the correct depiction. So this is your correct answer. Coming to the next question, which of the following is or are true regarding screw pump? So we already discussed screw pump is an axial positive displacement pump. Axial flow positive displacement pump. The option says it's a radial flow positive displacement pump. This is not correct. It produces pulsating flow. No, it produces a continuous non-pulsating type flow. It can deliver highest discharge among all types of positive displacement pump. Yes, this is correct option. Unbalanced axial forces demand usage of thrust bearings. This is not correct because the axial forces are balanced in case of screw pump. Unbalanced. So this is again not a correct option. No radial or bending loads. This is correct. There is no radial load or bending load. The liquid is moving forward, and it's not tending to bend you know uh, the screw basically. And it needs external priming and is intolerant to entrant air. It is again incorrect. It doesn't require external priming. It is a self priming type of pump, and also it allows minimal entrapment of air, and it can work if certain amount of air is entrapped. But other type of positive displacement pump, it may not allow that. It is a self priming. So these two options are correct. Which of the following are properties of G rotor pump? Yeah. So, as you know, what is a G rotor pump? It is a specific case of internal pump, special case of internal pump, but there are some characteristic differences. Some characteristic differences because in case of G rotor pump, you have an internal pinion gear, and then you have a ring gear. But in this case, there is no crescent shape divider, right? So why was this crescent shape divider used? It acted as a seal between the outlet and the inlet ports, the pressurized outlet and the less pressure inlet port. So to prevent that, we had to put this crescent. So in case of G rotor pump, how do we overcome that particular problem? Like the backflow of liquid that was minimized due to this crescent shape divider. So in case of G rotor pump, what we do, we keep very close fitting between the ring gear and the pinion gear. So the pinion gear is just having one tooth less than the ring gear. You can understand that fitting is very close. Like this gap is very less. So it's just like one tip that is less in case of the pinion gear, that is the internal gear, as compared to the external. So what happens, like let me just, so if the pinion gear is having say 5, we'll have only 60. So this is your 1, 2, 3, 1, 2, 3, 4, 5, 6. So you can understand that the tolerance is very less. I mean, sorry, the clearance is very less. So the liquid that is again, if it's rotating in this direction, then this is the suction point, and this is the delivery point, because the mating happens, uh, unmeshing happens here and meshing happens here. So the liquid flows in between this small portion. So you can understand that due to this very close fitting between the two gears, the liquid doesn't have sufficient gap to flow back from the high pressure region to the low pressure region. So it will be carried forward only. But in case of internal gear, motor, what happens? This particular thing may not be there, and hence the clearance is large. So to overcome that clearance, we have to put this crescent step divider. So driven gear has one tooth more than the driver gear. No, this is absolutely not, like, this is not possible. Also, driver gear has one tooth more than the driven gear. Oh, sorry, I'm sorry. I just said the opposite thing. Driven gear. The outer gear is the driven gear. So this ring gear is basically the driven gear, and the pinion gear is your driving gear. Okay. So driven gear, that is the ring gear, it is having one tooth more than the driver gear. So the first option is correct. Obviously, second is wrong. Crescent shape divider is used. It is not used. It is incorrect. Tips of the mating teeth of driver and driven gears establish a sealing between the pump chambers. As I discussed here, that there is very less clearance between the tips of the driver and the driven gear, and hence it establishes a seal and it doesn't allow the backflow of the liquid. This is correct. Different tooth profiles. So, different types of tooth profiles are generally used in involute. Mm, Sorry, in case of internal spark gears, some of the tooth profiles. Can you name a few of them? So generally, we use involute type of gear tooth profile. It is most widely used. Then we have cycloidal, then epicycloidal, hypocycloidal. So these are the different types of tooth profiles. You can go through machine design book to know about each of these type of gear profiles. I hope, like in your third year of BTech, you have come across this particular terms. And also, there are different design criteria for this type of gears. How to ensure a positive sealing in a vane pump between the vane and the cam ring. So we know that in a vane pump, like, it is also similar to the configuration of an internal gear pump with some functional differences. So we don't have a teeth here, although we have this particular, you know, chamber through which the liquid will be flowing, and the meshing and the unmeshing of the gear used to produce the inflow and outflow. In case of gear pumps, in this case, we have, so in this case we have veins. So these are my slots in which the veins are inserted. Veins are nothing but metal plates. I'm just coloring them in red. So what happens as this is rotating? This plates are initially inserted inside this. I hope you have gone through the videos. You must be knowing. So due to the centrifugal force, these vents, if you simply rotate them not inside the chamber but outside, they will come out, right? Tend to come out due to the centrifugal force. But in this portion where there is a close contact between the rotor, so this is your rotor, and you this is the stator part, or what do we call? It is a cam ring. So in this portion, it is not, the cam ring is not allowing this to come out. These veins to come out. So as soon as it is moving away from this position, so here the veins are getting space. to come out. So that's why now what happens? The veins will be like this. Like it will be coming out. Camera. Okay. It won't be like like it should be touching the camera. So what happens when the liquid is getting sucked in from here? It flows through these small pockets, and finally, upon reaching here, it uh, the pressurized liquid it will flow out. This is the low pressure, and this is high pressure. So the question asks how to ensure a positive sealing between this camering and this particular vein. So if we look at one vein, say, so if this is my slot, I am just exaggerating one particular thing here, and this is my surface of the camering. So this is the rotor, this is my camering, and I have a vein which is sitting here at stationary condition. Now what happens? As soon as this starts rotating, the rotor starts rotating. I'm just providing some curvature here. As soon as the rotor starts rotating, this will be pushed outside due to the centrifugal force. And by the action of that centrifugal force, what happens? It will go and try to touch here. But again, when the centrifugal force, like it is dependent on omega or the RPM, say n. So if n is more, then the centrifugal force is more, because your this value of v will be more. So mv square by r. So and v is again r omega. So so what happens if n is more? Then it is not a problem. It will this force will be more, so it will go and like it will touch here, and it won't allow the this pressurized liquid to be flowing to the gap here to this region. It won't allow that. However, when your speed is less, like the pump is operating at lower speeds, then what happens? If your pump is operating at a lower speed, then your centrifugal force will be less, and this particular vein won't be sufficiently coming outward. So there will be some gap here that will allow the pressurized liquid to travel from here to this point. And this is what will account for the QL or the loss component. To prevent that, what do we have to do? We need to provide some pressure over this region so that this vein and goes and touches this camering at these contact points, at each of these contact points, right? So some pressure should be applied here so that as soon as the vein gets the room to come out, it will go and touch this camering, and there is no clearance for the liquid to flow from here to here. So how do we do that? We apply some system pressure or some hydraulic loading is given, so that generally what is done, just showing here. Generally, this is done under low speed conditions. We have a bulb sort of configuration here, and there is some pressurized liquid. Okay, so this is your some pressurized liquid or fluid, I would say, not liquid. So that will apply pressure onto the vein end, the vein will go and sit here. Now you can understand that this pressure, like we can't put high pressure as much as we want, because when this particular thing is touching the camera, and again we have to keep in mind that the vein is tight, so the sliding will lead to high friction, and also it will lead to wear of this particular vein or the camering wall, and premature failure of this particular pump vein, right? So to prevent that, we generally change the configuration of the vein. So either we have to optimize this pressure value, we can't use whatever we want, so a balanced, or we can say partial loading can be used system, and then we can use a bevel edge, this type of bevel edge. So this will since this pressure is say this pressure is kept constant, so this contact area is less, the contact force will also be less. F is equal to P into A. So since this pressure is constant, then this force will be, A is less means force will be less. Okay. And there are other type of vanes also. Here also you can say that the wear component may become high because of the pointed tip. So for that, sometimes we use dual type of, like two bevel vanes like this. So these are like few things that are done as precautionary measures, where while we are using some pressurized, some hydraulic loading here, and that hydraulic loading is done to provide a positive signal. Coming to another numerical, so a vane pump is to have a volumetric displacement of this much millimeter cube. So let me just write it down. Volumetric displacement. Again, you need to see like the units. It's basically VT. So it's 6543.21 mm cube. It has a rotor diameter of 60.8 mm. So diameter of the rotor is 60.8 mm. Diameter of the cam ring is 86.2 mm, and the vane width is 60.8 mm. And what must be the eccentricity? So as we know, like from here, these two, this particular this particular rotor and this particular cam are not coaxial. There is some eccentricity between these two components, and depending on this value of E, the volumetric displacement will change. So basically, your VT is a function of E. So as E increases, VT generally increases. Okay, so let us find out the value of E. So we know that E is nothing but D cam ring minus D rotor divided by 2. Okay, so you can derive this particular equation. It's not something very difficult. So I'm just giving you some hints. So if these two are the circles, you need to find out this distance, right? So this much is your D cam divided by 2. and this much distance is your dr divided by 2. So simply, if you want to calculate this one, you have to subtract this dr by 2 from dc by 2. So this is your e, right? So one more thing, this is the maximum eccentricity that can be achieved. If you want lower eccentricity, what you will do, like maximum eccentricity, why I am telling, for this particular motor, this dc and dr are constants, right? Now you can use the motor in this configuration also. Sorry, in this configuration also, where there is some clearance here. You can use it like this, where there is complete clearance and these are coaxial. This you can understand that the eccentricity is less, and you can use it like this also. So as you may understand here, the eccentricity is less. Here the eccentricity is zero, and this is your E max. So in this case, there will be no flow of, no suction and delivery of fluid. Okay, suppose this is rotating like this, the veins will go and it will touch the camering like this. So you can understand that um, like this particular region and this particular region, the volume will be same. So there is no increase in volume and hence no suction phenomena happening or discharge phenomena happening. So it will simply, the liquid will recirculate within these pockets inside the pump. It won't be sucked or delivered. In this case, there will be some partial suction and delivery because the veins will, go and sit here onto the camering, and this particular region, uh, the volume is increasing in this direction, and hence the suction will take place. And in this particular region, as the volume is decreasing, the delivery will take place. But since the eccentricity is less, the difference between the volumes of this pocket will be less, and hence the amount of suction pressure will be less. So the discharge will also be less. In this case, the eccentricity is maximum. So the amount of suction pressure and the discharge pressure created, that will be like more for and hence the vt, the value of vt will be more. So now coming back to the numerical, this is just like shown here. What is the value of e? Okay, so this is nothing but your e max, right? 86.2 minus 60.8 divided by 2. How much are you getting? Calculator. 6.2 minus 60.8 divided by 2. 12.7. Now you see, like this, is this the the eccentricity that is being asked? Because when you are being said that like this will be the maximum value of eccentricity, but in the question it has nowhere been said that like evaluate the maximum eccentricity. They have asked you what will be the value of eccentricity. So if you try to calculate from vt, then like we know that vt is nothing but pi by 4 dc square minus dr square divided by W. You have been given okay, so from here, how can you proceed? Like you're having the maximum value of eccentricity. So when you're having condition like this, there is a shift from Emax to a lower value of E. You have a camering diameter given, vane width given. What must be the eccentricity? So let's apply this formula. Vt is equal to, so this needs to be true of this. So 86 2 square minus 60.8 square divided by 4 W 60.8. So if you try to see, like if you are having maximum eccentricity, so the value of Vt that you will get, that will be maximum. So what will be that? This Vt is not this particular thing. This is actual volumetric displacement. So if you try to find out Vt max, so that will be like you just try to calculate it once again. Pi by 4 multiplied by dc square minus dr square. So that's 86.2 square minus 60.8 square. Yeah, multiplied by the width, that is 60.8. So you will get around 1,78,297.19 mm cube. Okay. Now it has been asked, but as you see that the actual displacement is this much. So let's say, okay, so if we try to put it this way, Vt actual is equal to So this comes from like we are so that comes from the E for Emacs. So if we instead of putting Emacs, if we put E and try to see, then whether it's coming or not, like 6543.21. Okay, so we will just divide the entire, you know, this particular thing except the value of E and check. So let's see, 86543.21 multiplied by 4 divided by pi divided by DC plus DR. So that's 60.8 plus 86.2. 60.8 plus 86.2 can divided by 2 divided by W. W is 60.8. So by substituting all these values, we will be getting the value of E as 6.16 6.16 mm. So this is close to option C. So what I actually did is like for VT max, we are writing this particular equation. This particular equation is like it is constant, like it is applicable for like yeah. So this is applicable only when the volumetric displacement is maximum. Why? Because this is the area that we are talking about, right? So if we substitute the value of Emax here, like in place of this E, if we substitute the value of maximum, eccentricity, that is this one, then the VT will be VT maximum. That is nothing but this value, right? But we are seeing that we are having a value of eccentricity that is less than the maximum eccentricity. Like after solving, we are seeing that 6.16 mm, it is less than 12.7 mm. Why? Sorry, I mean, like what? By seeing what we can say that it is having lower eccentricity because this particular volumetric uh, displacement, that is 86,543, it is less than the maximum volumetric displacement that is possible. You can understand what we just discussed now. The VT is, it is dependent on the value of E. So your VT is basically directly proportional to E. If other parameters are constant, then as E increases, your value of VT will increase. Okay. So, this will be the last question for today. Which of this does not hold good for a vane pump? Vanes reciprocate inside the slotted rotor. So balanced type only, no. Unbalanced vane pumps and balanced vane pumps both exist. Vanes reciprocate. We won't say it reciprocate, rather it slides. But let's see the other options. Eccentricity between the cam ring and the rotor varies with flow rate. So if your value of key Q, that is again directly linked with the discharge sorry, it is directly so if Vt changes or Vt increases, Q also increases. And we have seen in the previous problem, and that is directly related with E. So eccentricity increases. So basically, it's just the opposite thing. I mean, I won't say that eccentricity is the effect of Q. It is rather like when the E is less, you are having lower Q, and when you're increasing the value of E, you're getting higher Q. Anyway, like they follow a direct relationship. Direction of eccentricity does not affect the direction of flow. This is wrong. Suppose this is your neutral position. You're showing it like this. So this is the center of the camering. Uh, this is the center of the rotor. So this is E. Say. When there is no E, it will look like this. So here E is equal to 0, and this is one case, and you have another case like this. So here we are providing the eccentricity downwards, and here we are providing the eccentricity upwards. So this is your E here. So you can understand that now we are rotating the rotor in this. Okay. So as we are rotating the rotor in this direction, what happens? This is the position where the um, suction will be taking place. Then it will flow like this, and it will get discharged. In this case, if the liquid is already inside, it will just recirculate like this. Otherwise, like it won't provide any suction because the value of E is 0. So that's why the Vt will also be 0. Here you can understand that the direction of flow will be from here to here. In this case, the suction will be from this side, and the delivery will be in this side. So basically, in this we are seeing that this is all these things are in the same plane, but it is not so. Generally, there are two different planes, like different planes for the. If we look at the side view, so suppose suction happens from here, and the delivery will be happening in this side. Okay, and in this case, it will be opposite. Suction will be from here, and delivery will be in this side. So it depends on like how we are placing the ports, and yeah, it is obviously dependent on the direction of eccentricity. So this is a wrong thing. An eccentricity between the camering and the rotor is independent of the flow rate. This is again like wrong. So these two, and this one also we can say it reciprocates, because yeah, it follows a sliding motion. So reciprocation is basically when you are having a constant value of you know sliding this amplitude is constant, about which it is sliding, but okay, like we can say it's reciprocating. Okay, so these were the questions of discussion today. If you have any other questions, we can take it up now. related to today's discussion or like previous day's discussion. In today's discussion, I have limited to when type of motors only. Other type of motors, such as your uh, centrifugal motors and like axial displacement, like non-positive displacement type motors, and also the reciprocating type motors are not discussed in today's discussion. We will take it up in the next class. If you have any other doubts, you can post them in NPTEL portal, and you can ask now. Otherwise, we will disperse. Do you have any doubts? Lokesh and Prem Kumar, do you have any doubts, or shall we close the session? Okay.
No, sir.
Okay. Yeah, Prem Kumar, you want to ask something?
No, sir.
Okay. Okay. You have registered for the exams, right? For this particular course, or you're just auditing it?
So I will register by tomorrow, sir.
Yeah. You can, like, if you want the certificate, then you have to write the exam.
Yes, sir.
Okay. Hmm.
Thank you, sir.
Hmm. Thank you.